Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study what is thin shells and some of the problems we are going to solve about thin shells. Let us begin with the course outcomes and Bloom's taxonomy related to this thin shells topic is the course outcome number 6. The course outcome is that make use of the concept of torsion and buckling of thin shells, spheres, etc. to determine the stresses at various points of geometry. The Bloom's taxonomy level is related to the apply level. Let's this introduction. What is introduction of the thin shells? Yeah, the unit. We are going to yes. What is the introduction? This unit presents the analysis of thin shells and spheres, thin cylindrical cells, and spheres subjected to internal fluid pressure. The thin shells examples are here steam boilers, reactors, nuclear containers, tanks, working chambers of engines, etc. are the common examples for thin shells. And what we are going to study in this chapter is that in this module is the stresses and strains developed on the thin walls of the cylindrical cells and how these stresses are developed. There are various types of normal stresses such as hoop stress and longitudinal stresses, how they are developed, and what about strains, volumetric strain, longitudinal strain, and circumferential strains, how they are developed when the fluid pressure is acted within the cylinder, within the cylindrical shell or spherical shell. So here, these are the thin cylindrical shells. We can see here the boiler, here the thin cylindrical the shell, which is having the larger diameter and small thickness. The ratio of the d by t, that is the shell that this diameter to thickness, that means diameter is equal to 15 times thickness or 20 times thickness. Then the cylinder is then the shell is comes under then the cylinder is comes under the category of thin cylindrical shell. There are thin shells which are used for the purposes of here using storing the gases or storing the liquids. But in this module, we're going to study, as I already mentioned, how when the fluid pressure is there inside the cylinder, how the stresses will be developed in circumstantially and also along the longitudinal direction. That's called along the longitudinal direction. It is sigma L longitudinal stress, and along in circumferential direction is the hoop stress. That's called hoop stress, and longitudinal stress is developed. So why should we do analysis? This stress analysis. Why should we find out? Because in order to design a robust or withstandable for these stresses, the cylindrical shell should be designed. At the same time, if you maintain the too much thickness or too much strength, then it leads to the cost of the product. So in order to minimize the cost, at the same time, these shells should withstand the maximum level of pressure levels, such a way that we have to design or we have to manufacture these cylindrical shells. So which are a very important factors, those two factors. So the material should not be wasted or should be utilized properly. At the same time, the shell should withstand for the stresses of that hoop stress and longitudinal stresses under the fluid pressure. The fluid can be a liquid and also gases. That's why these are should withstand. For the gas pipelines, the gas pipeline is such a way they make fabricated such a way that it can withstandable. Those pipelines can withstand the pressures. Otherwise, if the shells are not made of proper or optimized, diameter and thicknesses, there will be catastrophe takes place. Not only human loss and also material loss, manpower loss, and cost of the product. These are the various parameters are to be considered in order to design the hoop stress and for withstanding the hoop stresses and longitudinal stresses. Now here at the end of the session, the student should have the knowledge of stresses developed in the thin cylinders and various formulations such as for circumferential and longitudinal stress in those cylinders. And the third one is the basic design principles, and the fourth one is the joint design, that the welded or riveted joints. These are the four objectives the students objectives knowledge the students should have at the end of the session. That is the main aim for this lecture. Now, coming to the assumptions, there are various assumptions while designing or while studying and while doing the analysis of the thin cylinders. The assumption is that the diameter of the cylinder is more than the 20 times the thickness of the shell. That is diameter of the cylinder D equal to 20 times the thickness. That means the D by T ratio is 20. So our T by D ratio is 1 by 20. And the second assumption is that the stresses are uniformly distributed through the thickness of the wall. That means there will be homogeneity. And at the ends of the cylindrical shell, are not supported from sides. Okay, because they are completely closed here. The weight of the cylinder and that of the fluid contained inside are not taken into account. Here we don't consider the weight of the cylinder, and also the fluid contained inside are not taken into account. And final one is the reference pressure. Here the atmospheric pressure is taken as the reference pressure. So that is the absolute pressure here, that is the reference. By considering all these assumptions, 5 assumptions, we are going to derive the expressions for the stresses and strains of a thin cylinder. The expressions are what is the hoop stress and what is the longitudinal stress. Now here, suppose this is also boiler shell, example for thin shell. So it is not like the thin shell can be a cylindrical, it is a closed one. For boiler there are different attachments. Here it is the pressure gauge and safety valves and inlet port and outlet. So these are the various parts are to be attached for thin cylinder, because the pressure gauge indicates what is the level of the pressure inside the cylinder. And here the safety valve, when the pressure is exceeding beyond the factor of safety of the cylinder, the safety valve explodes, gives the pathway to release the gases or release the fluid inside the cylinder in order to prevent from the blasting of the cylinder. It is nothing but here the basic principle of this boiler is the steam exchanger or steam generator. Here we can see in the kitchenwares that's the pressure cooker. We consider the pressure cooker. In the pressure cooker, there will be a safety valve, at the same time the whistle. So the pressure cooker contains the lid such a way that the burner. So there will be a safety valve, at the same time whistle. So because of accumulated dirt or due to the pressure, if the whistle is blocked, then what will happen? This safety valve, it is made of lead. There, in that lead pot, it will be melted at low temperatures. The melting point of the lead is very low, such a way that it will be melted and drops down inside. Then immediately the pressure comes out in order to prevent from the blasting of the cooker. So like that, similar in boilers also. But here in this we study only without any completely closed cylinders. We'll study. There is no pressure gauges, there is no safety valves, nothing. So those shells we are going to study for as an idealistic to understand the circumferential stresses and the strains and longitudinal stress and longitudinal strains of the thin cylindrical shell. This is the picture. It indicates the blasting of the boiler, how the blasting takes place when improper, there is no safety factors here, the blasting. Because of this blasting, it likes though the manpower loss at the same time material loss and everything taken place. So to prevent such catastrophic failures, one has to design properly and do analysis by considering the circumferential stresses and longitudinal stresses inside so and so for a kind of the fluid pressure. The thickness of the cylinder and the diameter of the cylinder are to be decided based on the pressure, based on the fluid pressure, to avoid this kind of catastrophic failures. Now, coming to the case study, here this thin cylindrical vessel subject to the internal pressure is the closed cylinder. We can see here is the thin shell because d by t equal to 20. The diameter to thickness ratio equal to 20. That means diameter of the shell should be more than the 20 times the thickness of the shell. Now here the d is the diameter inside the diameter, internal diameter, where t is the thickness of the wall, and the fluid pressure is denoted by P. It is internal fluid pressure, and the length of the cylinder is the L. The total cylinder length is L plus 2 times T. Now similarly, total outer diameter of the cylinder is D plus 2T. Though if you see the side view, this figure A and figure B, if you see in the side view, the internal pressure is acting radially outwards here, how in the radial direction. So if you see in a front view, there are two views, front view and side view. Figure B indicates the side view, figure A indicates the front view. Here in this front view, if you see in front view, the sectional view, the fluid pressure, one is in the direction along in circumferentially it acts, and another one is towards outside along the longitudinal direction. So if we take sectional view in this direction, we can experience, or if we could take another sectional view. So these are the hoop stress can be seen. This is the hoop stress, and the longitudinal cut. If you cut a section in this way longitudinally, we can see how it is being taken place. So let us know some of the things where small d is internal diameter of the thin cylinder, and T is the thickness of the wall of the cylinder, small t, where P is the internal pressure of the fluid, and where L is the length of the cylinder. So on account of the internal pressure P, the cylindrical vessel may fail by splitting up any one of the two ways, as we are going to show you. So, but then how it will be split up? One is along the longitudinal off, and another one is circumferential off. So the forces due to pressure of the fluid acting vertically upwards and downwards on this thin cylinder tend to burst the cylinder in the figure A. This is the figure A, tend to burst. And the figure B indicates when the forces due to pressure of the fluid acting at the ends of the thin cylinder tends to burst the cylinder. This is horizontally if it acts, as we consider. This fluid pressure acts to burst in this manner. It bursts, so it becomes off piece. This is the word pressure bursting. And because of the pressure of the fluid along length, so it will burst the shell in this direction. So it will burst off. This is the cross sectional perpendicular to the axis of the vessel. This is longitudinal axis perpendicular to it. Okay. In the shell it will be in this manner. So these are the two failures. The cylinder, because of due to fluid pressure, the splitting up takes place in this direction. Now the forces due to pressure of the fluid acting vertically upwards and downwards on thin cylinder tend to burst the cylinder, as shown figure. This is the figure A. And another failure is that the failure of another one is here. The forces due to pressure of the fluid acting at the ends. The pressure of fluid acting at the ends of the thin cylinder then tend to burst the thin cylinder in this figure B. The figure B indicates this is the figure A. This is figure A. when pressure acts in this direction, pressure of the force, and when pressure of the force along the longitudinal direction, the failure splitting. So under these cases, the stresses will be developed. At the case A, at the figure A, the circumferential, if we consider it, the circumferential stress, if we consider the element. And if we consider this element here, the bursting takes place. The bursting place in the longitudinal stress, sigma L or sigma 2 or sigma 1, which depends on the notation here. Now, expression for the circumferential stress, or it is nothing but a hoop stress. We are considering a figure A. In figure A, it acts as the circumferential stress will be developed in figure A due to bursting. So, in order to maintain not to burst, what to do? It should be the internal pressure, the worst condition or the maximum optimum level should be the internal fluid pressure should be equal to the external, the circumferential stress will be developed in the circumference of the cylinder. So here we are considering the thin cylindrical vessel subject to the internal fluid pressure. The circumferential stress will set up in the material of the thin cylinder. If the bursting of the cylinder takes place as shown in figure A, this is a figure A, then the expression for hoop stress is obtained as given here. How it will be developed here? By considering that P is the internal pressure of the fluid, where D is the internal diameter of the cylinder, T is the thickness of the shell or thickness of the wall of the cylinder, where sigma 1 is the circumferential or hoop stress in the material. Now, this is the word here because of the stresses developed in upward and downward directions, P1 and P1 acting here. Now, this pressure is the sigma 1, that is the circumferential stress. Sigma 1 is the tensile direction, sigma 1, and the fluid pressure is acting on the surrounding, the radial, the fluid pressure. So, for equilibrium, the circumferential stress acting on the thickness of the shell and along the length, whereas the internal fluid pressure is acting on the circumference or internal diameter of the shell. Now, the bursting which takes place due to the force of the fluid pressure is more than the resisting torque or resisting force due to circumferential stress. So, this bursting takes place, the fluid pressure exceeds more than the resisting or more than the circumferential stress force developed by the circumferential stress. So, then it takes place, so the two forces should be equal, so that that is the limiting condition. So, what is the force due to fluid pressure? The force due to pressure equal to pressure times the area. The pressure times area on the P is acting. The pressure times area, that is D times L. This is the D and length is L. D times L, that is P into DL. Now, the force due to circumferential stress, then that is equal to circumferential stress times the area. What is that area here? L into thickness. This is the length L and the thickness. There are 2 times LT. Sigma 1 into 2 times LT. So, 2 times sigma 1 times LT. If we equate these two equations, P into D into L equal to 2 sigma 1 times L into T. Now, sigma 1 from this simplification, L will be cancelled, then PD by 2T. Sigma 1 equal to, by cancelling the L on both direction, L and both left hand side and right hand side, the sigma 1 equal to PD by 2T. So, this stress is the tensile stress. That is nothing but the direction of the stress is going away from the cross section. It is in tensile in nature. The stress is known as the circumferential stress. The circumferential stress sigma 1 or sigma H equal to PD by 2T. What is the P? P for internal pressure, D for internal diameter of the thin shell, and T is the wall thickness. So the unit for P is that the internal pressure, that is in Newton per square millimeter unit pressure, whereas the internal diameter of the thin shell, it is in millimeter, where T is the thickness of the wall thickness, that is in millimeter. So finally the stress, if we cancel here, the unit of the circumferential stress, sigma h, is in Newton per square millimeter. So in this manner, we have to derive the expression of the hoop stress for the conditions of internal when the internal fluid pressure is acting of the thin shell. Now coming to the second case, we are going to study the expression for longitudinal stress. Expression for longitudinal stress, that is a force due to pressure. This longitudinal stress, the stress is acting in longitudinal direction. The stress is acting in longitudinal direction, but provided, how can we know? The sectional view is the section is AB, is the section plane, where T is the thickness. Where T is the thickness, wall thickness. This pressure P is acting along the length on the top and bottom face of the cylinder. If the top and bottom faces, we keep the cylinder vertical direction, the pressure acts due to this longitudinal, this pressure in this direction at the top and bottom. Because of this fluid pressure, what happened? The internal fluid pressure, the longitudinal stresses will be developed here. The longitudinal stress developed sigma L and sigma L. Now if you cut the view, the section AB plane, the longitudinal stresses will be developed along, not to break the part into two pieces. So that's why here now the sigma 2 is acting on the circumference here. So pi d times t, pi d times t, sigma 2 times pi d into times. Now the fluid pressure is acting here, this zone. This is the zone fluid pressure is acting. What is the fluid pressure? P times P is the pressure times fluid pressure force equal to pressure into area, that is pi d square by 4. Here the force due to fluid pressure, what is the limiting case condition? When the bursting takes place, the bursting takes place when the internal fluid pressure force, the pressure force is greater than the force developed by the longitudinal stress. When it exceeds the force developed by longitudinal stress is greater than the longitudinal stress per force, then the bursting takes place. So what is the limiting condition? If you equate the force due to the pressure equal to force due to the longitudinal stress, force due to internal fluid pressure, that equal to internal pressure times area on which P is acting. The area on which acting, this is the area on which the P is acting. So the area on which acting, this is the area on which it is the P is acting, that is the P into pi d square by 4, where D is the diameter of the shell, the diameter of the shell, this is the portion D. Alright, that is P into pi d square by 4. Then next, now what is the resisting force? The resisting force is sigma 2, that is longitudinal stress times area on which sigma 2 is acting. The area on which sigma 2 is acting, this is the area. This is the area on which sigma 2 is acting. The sigma 2 times pi d times t, circumferential area, that is sigma 2 times pi dt. Now P times pi d square by 4 equal to sigma 2 times pi dt. Now we equate by cancelling the d on both sides and pi both on LHS and RHS. Then what will happen here? Sigma 2, the longitudinal stress, equal to PD by 40. PD by 40. Sigma 2 or longitudinal stress equal to PD by 40. Now PD by 40, this sigma 2, what is the nature of this longitudinal stress? The longitudinal stress here, it is in tensile nature. So it is also in tensile, and circumferential stress also in tensile. There is no compressive stress is here, it is acting. Now sigma L, the longitudinal stress, that is PD by 2T, that is 1 by 2 times PD by 2T. What is the PD by 2T here? That is the hoop stress, sigma H. So the longitudinal stress, sigma 2 or sigma L, equal to sigma 1 by 2 or longitudinal hoop stress by 2 of the hoop stress. So the longitudinal stress, the value of the longitudinal stress is half of the hoop stress. The value of the equation of the longitudinal stress is half of the circumferential stress or hoop stress. So that's why sigma 2 or sigma h, longitudinal stress sigma L equal to sigma h by 2. So if we know the hoop stress value, then the half of that hoop stress value is nothing but the longitudinal stress value, the value of the longitudinal stress. Now, the next is that not only the circumferential stresses will be developed, what about shear stress? The shear stress, because of shear stress only the splitting takes place because due to normal stresses. So the maximum shear stress tau maximum equal to sigma 1 minus sigma 2 by 2. What is the sigma 1 here? The tau maximum. Sigma 1 minus sigma 2 by 2. What is sigma 1? Sigma 1 is nothing but hoop stress. Sigma 2 is longitudinal stress by 2. What is sigma h? That is PD by 2T minus PD by 4T by 2. Then the final it comes as PD by 8T. The maximum shear stress is PD by 8T. Now here we can develop the relation if we know the hoop stress. In terms of the hoop stress, sigma h equal to PD by 2T. Then sigma L equal to half of, that is sigma h by 2, half of sigma L. Now what about tau maximum? The maximum equal to sigma h by 4. Sigma h is the PD by 2T. Longitudinal stress is the half of the hoop stress. Maximum shear stress is 1 by 4th of the hoop stress. So these are the relation between hoop stress. So if we know the hoop stress, we can know the value of longitudinal stress, and also the shear stress can be also be known. The value of the shear stress can be known. So maximum shear stress is 25% of the hoop stress, of 1 by 4th. Or in another direction, sigma L equal to, that is the 50% of sigma h. Tau maximum is 25% of sigma h. That means 50% of sigma h is longitudinal stress, and maximum shear stress is the 25% of the hoop stress value sigma h. So in that manner we can know the values of longitudinal stress and the maximum shear stress developed, provided the hoop stress, the value of the hoop stress is known. Sigma h is known. If you know the sigma h, sigma L and maximum shear stress can be known. Next, now here let us solve some of the problems to understand the reason, how to apply those problems, those formulae, derived expressions in order to find out the longitudinal stresses and circumferential stresses developed in the pipe or in the thin cylinder. So in this problem here, a cylindrical pipe of diameter 1.5 meter and thickness is 1.5 centimeter is subjected to an internal fluid pressure of 1.2 Newton per square millimeter. Determine the longitudinal stress developed in the pipe and also circumferential stresses developed in the pipe. So the given data here, let us write down the diameter of the pipe is 1.5 meters and thickness is 1.5 centimeters. That is nothing but 1.5 times 10 power minus 2 meters. So we have to know it. We have to know whether the diameter, whether is this a thin shell or thick shell. So if we make it a T by D ratio, that should be more than the 1 by 20. That should be less than 1 by 20. Or D by T ratio, the D by T ratio should be more than 20. So make it the ratio, D by T ratio, that is around 100 will come. D by T 1.5 by 1.5, that is 100. That means more than 20. That means this cylinder is the thin cylindrical shell, thin shell. Now we have to apply the formula, derived expressions related to the thin shells. So the longitudinal stress, that is sigma 2, that's what they asked, that is sigma 2 equal to PD by 40. That sigma 2 equal to PD by 40. We know the internal pressure value, that is 1.2. What is the internal diameter? The inner diameter is 1.5. So this is 1.5. 1.5 internal diameter, that is 1.5 meters. So convert into millimeter, that is 1.5. Then it becomes next 4 times T. What is the thickness? 1.5 into 10 power minus 2. Here 1.2 directly, that means here the value of the internal pressure is 1.2 Newton per square meter. That's what meaning is here it is. So 1.4 Newton per square meter, what will happen here? If you substitute all the units should be no dimensional homogeneity, then the value will come here it is converted into meters. 1.2 should be internal pressure P equal to 1.2 Newton per meters. 1 millimeter equal to how much it is? 10 power minus 3 whole square, that is meter square. Now go stop, then 1.2 into 10 power 6. Then if you substitute all values, then it comes as 30 Newton per square millimeter of converting Newton per meters. Or we can make it here 1.2 Newton per square meters. This is 1.5 meters into 10 cube by 44 times 1.5 into 10. Then the value is obtained as 1.5, 1.5 cancel. Then it becomes 30 Newton per square millimeter. Now whatever next the value of the circumferential stress, the circumferential stress sigma 1 equal to PD by 2T. And substitute again the values, the known values of the internal pressure and the P and the internal diameter and thickness. Then we can get it as 60 Newton per square millimeters. So these are the values of sigma 1 and sigma 2. Here you may get here 1.2 is in Newton per square meter are considered here. That's why it become, but answer is in 30. Better to substitute here PD by 2T, whatever book may be. What is internal pressure? P is the 1.2. Consider it is Newton per square millimeter. D 1.5 into 1000 by 2 times T. 1.5. It is in centimeters. Convert into millimeters. It is everything is in Newton per millimeters. Now this value is considered. That is 0.6 times. Yes, 0.6 times 100, that is 60 Newton per square millimeter. Alright. So in that manner we can get by using this formula derived expressions of circumferential stress and longitudinal stress, we can calculate the values of them. Now that's what here. Now we can validate the circumferential stress is, or the longitudinal stress is off of the circumferential stress. So the longitudinal stress value is the 30 Newton per, it is and the circumference is 60 Newton per square millimeter. So the longitudinal stress value is off of 60 by 230. Yes, we got it here. Now the next model, we are going to next problem. Let us go for the next problem. Next problem is that a cylinder of internal diameter 2.5 meters and thickness is 5 centimeters contains a gas. Here the fluid, internal fluid is the gas. If the tensile stress in the material is not to exceed 80 Newton per square millimeter, determine the internal pressure of the gas. Determine the internal pressure of the gas. So now here the internal diameter is 2.5 meters and the thickness is 2.5 centimeters. That's 5 into 10 power 5 times 10 power minus 2, that is also in meters. The maximum permissible stress, that is in 80 Newton per square millimeters. Now, what is the maximum? Determine the internal pressure of the gas. We want internal pressure P. What is that? Now, the maximum permissible stress is given that the value is 80 Newton per square millimeter. So, the maximum permissible stress is nothing but a circumferential stress. because the circumferential stress is the maximum value in comparison to the longitudinal stress and the maximum shear stress developed. Why? Half of the circumferential, that is the stress, equal to longitudinal stress. That's why we have to consider the maximum permissible stress value is nothing but the circumferential stress value, that is sigma 1. Now we know the sigma 1. Now then what we do here, we know the circumferential stress should not be greater than the maximum permissible stress. So now that sigma h is the 80, nothing but the maximum permissible stress, that is 80 Newton per square millimeter. Now P is the internal pressure of the gas. Now sigma 1 equal to PD by 2T. Now PD, what is the internal pressure? From that P equal to 2T times sigma by D. Substitute here all the values, then we'll get it the value of what the P equal to 2T times sigma 1 by D. What is 2 times T? The T is 5 times 10 power minus 2, or you can consider the 50 millimeters, 2T times sigma 1. The sigma 1 is in 18 Newton per square millimeter, and the D is 2.5 meters, that is 2.5 times meters 1000. Then if we simplify here, then you get it after calculation. The internal fluid pressure is 3.2 times Newton per square millimeter, or 3.2 times 10 power 6 pascals, or 3.2 times megapascal. So the internal pressure should be 3.2 megapascal. If it crosses the limit of this 3.2 megapascal, immediately what will happen? Bursting takes place. In what direction? Circumferentially bursting takes place. That's what value we have calculated here. Okay. And the next problem here it is, a cylinder of internal diameter with 0.5 meters contains pressure of 7 Newton per square millimeter gauge pressure. If the maximum permissible stress induced in the material, again it is in 18 Newton per square millimeter, find the thickness of the cylinder. Here what to be found? The thickness T. In before problem we found the pressure value, what is the internal fluid pressure. Now the internal diameter is D equal to 0.5 meter and internal pressure of H, that is P equal to 7 Newton per square millimeter. Now the maximum permissible stress, as we have studied, that is nothing but a circumferential stress. That is now circumferential stress, again here sigma h or sigma 1 equal to PD by 2T. The PD by 2T we want T, that is T is nothing but PD by 2 times sigma 1. Now substitute here T equal to PD by 2 times sigma 1. What is the P here? 7 Newton per square. What is the diameter? That 0.5 times 10 cube. It is in millimeters. 2 times sigma 1. The sigma 1 is 80 here. Now substitute all the values. The calculated the thickness is 21.88 millimeters. So these are the 3 varieties of problems we have solved by using the expressions which were derived in this session. The expressions were derived for a thin cylinder is that one is the circumferential stress, that is sigma 1, nothing but that is called PD by 2T, and another one is the longitudinal stress, that is PD by 40, and the maximum shear stress is the PD by 80, 8 times thickness. Now what are the basic equations are here? What are the basic things? What are the definitions we followed here? Important definitions in order to solve the problems or understand the knowledge here. Here D by T ratio, the diameter of the thin cylinder, internal diameter and the thickness of the wall of the cylinder should be more than 20. Then that type of cylinder is known as the thin cylinder or thin shell. The second one is that another manner, that is the T by D, should be less than 1 by 20. that is thickness to diameter, this diameter to thickness. And the third is the circumferential. The splitting up, the bursting takes place in two directions of a thin cylinder, of a closed cylinder. Along the longitudinal axis, that gives the sigma h, and along the circumferential, that is here in this direction, the bursting place with two places, this is the longitudinal stress gives. What is the circumferential stress? Sigma h equal to the internal pressure P and the thickness is T, and then the diameter is small d. Then sigma h equal to Pd by 2T. And sigma L, longitudinal stress, that equal to Pd by 4 times thickness. And the maximum shear stress developed, that equal to Pd by 8T. What is the T here? What is the T is the wall thickness. The units for wall thickness, T is in millimeters. Units for internal diameter, D equal to, that is in millimeters. And the internal pressure, P is in Newton per square millimeter. Then finally the stress developed, whatever stress, the stress is developed units is Newton per square millimeter. So now very important definition here it is 1 megapascal equal to 1 Newton per square millimeter. How it comes? 1 megapascal equal to 1 into 10 power 6 pascals. 1 into 10 power 6 pascals, that means Newton per meter, square meter. That means 1 into 10 power 6, 1 meter equal to, again, 1 meter equal to 1000 millimeters, that is 10 power 6 millimeter square. So get cancelled, that is 1 megapascal equal to 1 Newton per square millimeter. So these are the definitions, important definitions here we have studied. Now these are the important to understand the circumferential stress and longitudinal stresses, and also the maximum shear stress developed in the thin shell. Now various things, these are the references for follow textbooks, and here the strength of meteors by R. Subramaniam, here R. K. Bansal. You can see it here, web references. With this we can conclude the session. In this session, let us summarize. We have studied what is a thin shell, what is the definition of a thin shell, how can we justify, how can we know whether the shell is a thin shell or thick shell based on the internal diameter and thickness of the shell. And we derived the expressions or stresses in order to understand, in order to fabricate the optimum thin shell. We have to know the two parameters. One is longitudinal stress, another one is hoop stress, and the third one is the maximum shear stress. These stresses or expressions are derived in this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.